Welcome back, everyone, to our lecture series, Math 1210, Calculus 1 at Southern Utah University. As usual, I am your professor today, Dr. Andrew Missildine. This part of our series is Lecture 36, which we entitle Curve Sketching. The examples from this lecture are derived from examples from Calculus by James Stewart. In particular, these examples are coming from section 4.5, Summary of Curve Sketching. So what do we mean by curve sketchy? It sounds a little sketchy to me, right? I'm sorry, it's a horrible pun, but I have to try it anyways. So based upon what we've learned over the last couple lectures here in our chapter 4 of Stewart's calculus here, we've been learning about applications of the derivative. In particular, as we've been talking about L'Hopital's rule, extrema, max and mins, and how the first and second derivative affect the shape of the graph, we want to put all of these together and see exactly why does a function's graph look the way it does. Turns out the algebraic formula that gives us the function says so much about it. It's not just some random string of points. The behavior of the function indicates how this graph is going to be shaped here. So if we follow along with the same suggestions that Stewart offers in his calculus textbook, we have a list of things, A through E, that go into a good curve sketch. So how does one sketch the graph of a function f? All right. So the first on our list is the idea of domain. We should know what the domain of the function is. And so the domain, remember, these are going to be all of the possible x coordinates. And you'll apologize for my horrible handwriting, but, you know, it's what happens here. So we want to figure out all the possible x coordinates that go onto the graph. And by the domain convention that we've talked about previously, we're going to assume the domain is as large as possible, meaning that we accept all possible x's such that the formula makes sense for those real numbers x. Now, there might be some situations like we have a piecewise function, or we might specify the domain otherwise, but unless otherwise stated, we assume it to be as big as possible. So some things we have to watch out for. We don't want to divide by 0, right? When we have a rational expression of some kind, if you divide by 0, this typically gives us some type of vertical asymptote. We'll talk about these a little bit more in a little bit, but vertical asymptotes often happen from division by 0. We have to look out for like square roots of a negative. This will give us imaginary numbers. Likewise, if we take the log of a negative, same basic problem. But I should also mention that the natural log of 0, or any log at 0, is going to be undefined. These are the three main problems we have to look out for. Division by 0, square roots of a negative, and of course, when we talk about a square root, it's really just any even root, right? If you take a fourth root of -1, that's equally a problem. So we want to make sure we avoid even radicals of negatives, and any logarithm of a negative or 0 is also problematic. Now, admittedly, the trigonometric functions have some restrictions on the domains, like tangent, secant, but if you view those as quotients, they apply by the division by 0 rule applies there. So I'm not going to make much effort about that. The inverse trigonometric functions also have some restrictions, but we'll be honest, we're not going to be graphing those functions, so I'm not going to pay much more attention to them. So look out for the domain of these things. The range, on the other hand, like all the set of all possible y coordinates, that's a much harder question to answer. And in fact, by curve sketching, we'll actually learn very well how to identify the range of a function. But I would recommend start off with identifying the domain of these things. The intercepts, excuse me, part B. Intercepts are an important part of any graph because the intercepts tell us where does the graph touch the x-axis or the y-axis if it touches at all. We're going to use the x and y-axis to give us frame of reference as we're graphing these things, so it's nice to know their intercepts. A y-intercept is pretty easy to come by. If you want to find the y-intercept, you just have to look at the point f of 0 and then compute the corresponding y-intercept, or the y-intercept will be just f of 0. That's how you find it. So those are pretty straightforward. Your graph will have one y-intercept, except for if f of 0 is undefined. It could be that x equals 0 is outside the domain. X-intercepts are a little bit more challenging Because one, there could be multiple x-intercepts, and to find x-intercepts, we actually have to solve the equation f of x equals 0. And that could be more challenging depending on the nature of the function. Like if f is a polynomial function, like we'll see in a little bit, we might have to factor it. We might have to use other algebraic tools to help us there. And so finding the x-intercepts will be important for us, but this is one of the harder parts of the problem, finding the x-intercepts. There could be lots of x-intercepts, there could be one, there could be none. It depends on the function. And we'll see some examples to show you how that works. The notion of symmetry. Well, what do we mean by symmetry here? Well, there's a couple different types of symmetry we've talked about this semester already. So one of the types of symmetry we've talked about is the idea of even symmetry. When your function is, we'll say, symmetric with respect to the y-axis. That is, if we reflect the graph across the y-axis, we get the exact same thing again. This is the geometric interpretation of symmetry along the y-axis. I mean, what an even function is. Algebraically, we can find out this symmetry by looking at f of negative x. Because algebraically, if we replace x with negative x, we get a reflection across the y-axis. If the function's even, this should then look just like f of x. That is, it's unaffected by that change. Going hand in hand with even symmetry, there's the notion of odd symmetry. Odd symmetry is when you are symmetric with respect to the origin, right? Origin symmetry meaning that if you were to go through the origin, you would come out the exact same distance on the side. Or another way I like to think of it is if you were to rotate the function around the origin 180 degrees, a half spin, this gives you the same graph again. Algebraically, we can test for symmetry by looking again at f of negative x, and we get negative f of x, like so. And so the idea here is that if you were to reflect the graph across the y-axis, that's the same thing as reflecting it across the x-axis. Now, when it comes to these two types of symmetries, there's a simple test that we do for symmetry. You look at f of negative x. And so you look at f of negative x. If it turns out f of negative x simplifies just to be f of x, you're even. If it simplifies to be negative f of x, then you're odd. And if neither of those things happens, well, then neither of these two symmetries are exhibited on the function. Now, I should mention there is one other type of symmetry that is mentioned here. The idea if you're periodic. So it could be that you have a function which, if you take the function f of x and you add some period p to it, it might repeat itself after a while. The idea is like with trig functions, if you take sine of x plus 2 pi, then this thing just repeats itself. In fact, adding 2 pi to the angle doesn't make any bit of difference to it whatsoever. So trig functions are periodic, and those are the types of periodic behavior that we'll be really interested with the trigonometric functions. There's really not going to be other type of periodic functions we have here, but that is a type of symmetry I would like to mention. Because after all, if you know how to graph one period of a trigonometric function, you can just replicate that over and over and over again, and that gives you the whole picture. So knowing the period of a function, if it has one, can be helpful in simplifying the graph here. And that's kind of the reason why we care about symmetry in general, is that if we know the function is symmetric of any kind, if it's an even function, then I can just take the right-hand side of the graph and copy it, and that gives me the whole graph. So I basically only have to graph half of it. And if the function's odd, same basic thing, you have to rotate it, but if you can graph the right side of the graph, you get the left side for free. So this can be useful when you're graphing, but honestly, symmetry, in my opinion, doesn't play too much of a benefit as we curve sketch here. Again, it's useful, it is, don't get me wrong, but if you don't put a lot of emphasis on symmetry, I'll be okay with that. I'm just kind of following James Stewart's list here. But again, I do recommend symmetry. It's good, but it's not the most important thing. Discontinuities is going to be a pretty important thing for us. That I can't emphasize here, that if your graph has any type of discontinuities of some kind to it, I want to see that as you draw your graph of the function there. And we've learned in the past a couple different types of discontinuities, and so there's 3 discontinuities that I want you to be looking for as you're drawing your functions here. So the first kind, if you remember, was what we called the removable discontinuities. And so visually, this was the case that there was like a point missing on the graph. Some hobbit stole it from us, right? And so it could be that the point's just missing, or maybe it got moved to be somewhere else. There's a couple of ways this basically these are one of the two pictures you get. Either the point was removed or it's just missing in general. This happens when the limit of our function it exists, but for whatever reason it doesn't equal the function at that value. I guess I should probably add a limit here as x approaches a. The limit exists, but it doesn't equal f of a. And that could be because either f of a is a different number, or it could be that f of a is just missing entirely. Someone might, again, have moved it, so there's no point there at all. And so this is a removable discontinuity. Those are sort of the most benign type of discontinuities, but if your graph has any of those, we want to see them. All right. What was the second type of discontinuities? The second type is what we call a jump discontinuity. Jump of some kind. And so maybe your function was coming along and then it jumped, maybe because it's defined as a piecewise function. And so there actually might be this gap that lives between the function. You're going to get a jump discontinuity because with your function, as you're approaching, say, x equals a, if you come from the left-hand side, this might disagree with the limit from the right-hand side. And so this is what we have. This is when we get a jump discontinuity. If our graph has one, I want to see it as you're graphing it. All right. And so I'm trying to kind of erase things to keep everything organized here. By all means, if I'm going too fast, please pause the video and copy things down if you need it for your notes here. The last type of discontinuity that I kind of mentioned earlier, but the idea of a vertical asymptote. This is a long word, isn't it? Vertical asymptote. The vertical asymptote, the idea behind that is we might have some vertical line that our function is avoiding for whatever reason. Maybe you get something like this going on, something like this. Probably because this line is outside the domain, although that's not always required. And so our functions can be avoiding it as it goes. It's going to be going off towards infinity or negative infinity. So a vertical asymptote occurs whenever x approaches a from the left or right, f of x here, we get plus or minus infinity. Now, it doesn't have to be that both the left limits and the right limit are infinite, but we need something like this for a vertical asymptote to occur. And so these are the three types of discontinuities that we are looking out for. Jump discontinuities, removable discontinuities, and these vertical asymptotes. All right. So in behavior, what do we mean by this? In behavior, we're trying to figure out what does the function do as it goes to the extremes, as it goes to the extreme of its domain, which oftentimes that'll be negative infinity or positive infinity. And so like with a polynomial, is it going up on the right-hand side? Is it going up on the left-hand side? Maybe it goes up on the right-hand side, but down on the left-hand side. These are the type of questions we're trying to ask ourselves. So what's the limit as x approaches plus or minus infinity? Right, what is that? That's what we mean by end behavior here. Now, oftentimes, this might be plus or minus infinity itself, or it might be a finite number. If this limit turns out to be finite, that's because we have a horizontal asymptote. And so if that asymptote exists, include that on the graph as well. Now, another issue that does come up here is what if your domain's not negative infinity to positive infinity? Like if you took, for example, the natural log, y equals the natural log here, its domain is actually 0 to infinity, in which case we do care what happens as x approaches infinity. But on the other hand, the left-hand side, we actually care what happens as you approach 0 from the right. And so end behavior depends on the function. As you go to the extremes, what's happening to our function. We want to make sure we put that on our graph as well. All right, what does the first derivative have to do with graphing a function? Well, as we've seen before, whenever your first derivative is positive, this is exactly when your function is increasing. And when your first derivative is negative, this is exactly when your function is decreasing. And so this type of monotonic behavior is essential to know as we graph our functions. And we also want to keep our eye out for extrema, right? Do we have a local maximum, a local minimum? we should put those on the graph if they're there. Extrema will be something I absolutely look for on graphs. Just make sure you have the appropriate extrema there. We can say similar things with the second derivative, right? Because with the second derivative, if it's positive, this means your graph is concave upward. If your second derivative is negative, that means your graph is concave downward. And lastly, I'll be interested in those points of inflection. And we'll see some examples where we go through all of these in just a second. Points of inflection, we're going to care about those. And so we'll see some sign charts to handle all of those. And so in the end, once you have all this information, I want you to plot this stuff on some grid lines here. So if there's intercepts, plot them. If there's critical numbers, inflections, put those on there. In behavior, draw it. What else do we have on our list? Discontinuities, put them there. So plot all the points. And then the very last step is one of the most critical steps, because the function otherwise, except for those points that you've looked at, is going to be smooth and continuous. You can smoothly connect the dots. I know it sounds like a kindergarten skill, but turns out kindergarten is actually college level mathematics, right? We have to appropriately connect the dots here. And so these steps will help us as we try to sketch a curve here. So let's look at an example here. Take the function f of x equals x cubed plus x squared minus 5x plus 3. This is just a good old polynomial function. How can we graph this function right here? Well, when it comes to polynomials domain is always pretty easy. The domain of this function will always be all real numbers, negative infinity up to infinity. There's no situations where you can divide by 0, no square roots, no logarithms. Its domain will be all real numbers. Intercepts are can be a little challenge at times, right? The y-intercept, like I said, it's not too difficult. The y-intercept, well, we just have to look at f of 0. And when it comes to a polynomial function, the y-intercept is just going to be this constant right here, because when you plug in 0, everything else will disappear. And so the y-intercept will just be that constant right there. So let's write it down for future reference. We get y equals 3. X-intercepts are going to be a little bit more challenging because we have to solve the equation, like we said before, f of x equals 0. F of x equals 0. Now, for the most part, the homework is going to give you things that factor super easy without much difficulty to them whatsoever. This example right here is a little bit of a challenge. It's not at all obvious how to factor this thing. There are some techniques, and I would recommend you go to the lecture notes if you want some more examples. Or not more examples, but if you want to see the details how one factors this thing, please read these in the lecture notes here. But if one goes about factoring this thing, you see that it factors as x plus 3 and x minus 1 squared. So this tells us specifically that our x-intercepts are going to equal negative 3 and positive 1. All right, and our y-intercept here was 3. Now, I'll be honest, when it comes to James Stewart's list right here, I go out of order all the time. And so, honestly, I like to plot things along the way. Don't necessarily wait until the end. So we know that there's x-intercepts at negative 3 and 1. So let's actually put those. I have some grid lines down here. So what did we figure out here? It had an x-intercept at 1. So I'm going to draw a dot right here at 1. And it's a good idea to label your picture so it's clear to everyone what you have here, 1, 0. We had an x-intercept at 3, didn't we? Negative 3, I mean. So we get negative 3, 0. And then we also had a y-intercept. It was at 3. Get a picture like this. And then, so that's 3, 0, 3. All right. And so we'll come back to this in just a second. So we've plotted the x-intercepts and the y-intercept. So let's come back up to symmetry. Well, with our function, we can test for symmetry. You can take f of negative x there, but really there's not going to be any symmetry for this function. Again, I often just skip this step personally. If it doesn't become immediately obvious to me whether there's symmetry or not, I just kind of run away from symmetry. Sorry, but it's reality. If you take f of negative x, that doesn't simplify to be f of x or negative f of x. In terms of discontinuities, well, it's a polynomial, so it's continuous, right? There's really no issues to do with discontinuities here. things that we should look out for with discontinuities is going to be dividing by 0. That often gives us a discontinuity. Jump discontinuities will come about oftentimes from a piecewise function, so not a lot to worry about there. In behavior, well, when it comes to a polynomial function, the in behavior is determined entirely by the leading coefficient, or the leading term, I should say. Since you have this x cubed as the leading term, as x goes to infinity, you're going to get that x cubed approaches infinity as well. And as x approaches negative infinity, x cubed will approach negative infinity as well. And that's because odd powers will keep the sign. So if you go to negative infinity, odds will go to negative infinity. Even powers will always go to positive infinity. And so for polynomials, you just have to look at the leading term there. All right, let's start now with our first derivative here. Now, unfortunately, we can't see the original function, so let me write it back on the screen for us right here. So our original function was x cubed plus x squared minus 5x plus 3. So this was the original function y. So as we calculate y prime, we can just use the usual power rule, in which case we get very quickly y, 3y squared plus 2x. I'm sorry, why did I say y? 3x squared plus 2x minus 5. And as we want to find the critical numbers, we need to figure out what makes this thing go to 0. This is a quadratic polynomial. This one takes a little bit more to factor. Again, you can use the quadratic formula. You can use some various techniques of factoring, like this factorization by groups applies right here. And I'm going to refer you to the lecture notes if you want to see some more details about this right here. And again, for anyone who's not sure, there is a link in the description of the video for the lecture notes where you can get the script that I'm following right now. You can download it from my website. But if you factor this thing, you'll end up with x minus 1 and 3x plus 5, which then tells us that our critical numbers are 1 and negative 5/3. Now, this might feel a little bit like deja vu, but it's like, wait a second. X equals 1. We saw that one before. It was an x-intercept, but it could be that an x-intercept is also a critical number, not a big deal. Now, at this moment, we could start to do the first derivative test to help us know whether these are extreme values, maxes, or mins. But we're actually going to do the second derivative test in just a moment because we're going to calculate the second derivative. And therefore, we'll actually come back to these things to determine whether they're max or min. Now, with respect to these points right here, we do want to graph these critical numbers, whatever they turn out to be, maximum or minimum. If it's a max or min, we want to graph them. So we are going to have to compute y equals f of 1. We already know that's 0. We also have to compute y equals f of negative 5/3. That one's not as obvious. You'll have to do a calculation there. It's going to turn out to be 256 divided by 27. Feel free to use a decimal right here if you want to. And so before we go on, I do want to graph those critical points on the graph right there. We already had one x equals 1, right? That was one of them. So let's do the other one. The x coordinate was negative 5/3. Just so you know, negative 5/3 is really close to negative 2. So we're going to draw a little bit to the right of negative 2. And then the 256 over 27, that's a tiny bit bigger than 9. So we're going to draw that just about right here. This is our critical one. And again, label all the points, negative 5/3, comma, 256 over 27, like so. And so already with these dots we have right here, we have some x-intercepts right here and right here. We have a point. I'm already sort of believing that it seems very likely we have a local maximum right here. But again, we'll go through the whole derivative test to make sure as we talk about the second derivative here. All right, so for the second derivative, we have to take the derivative now of the derivative. So y double prime is going to equal 6x plus 2. This should equal 0, for which you can divide everything by 2 because 6 and 2 are both even. So we get 3x plus 1 equals 0, 3x equals negative 1, and then x equals negative 1/3. And so this right here represents our PPI. That is a potential point of inflection. It could be an inflection point. We don't exactly know yet. We're actually going to build our sign chart to help us with this information here. Now, in the meanwhile, we could start graphing this thing. We have this x equals -1/3. It'll be useful to compute its y coordinate. When you're looking for y coordinates, you're always going to put this back into the original function. The original function f of -1/3. That one turns out to be 128/27. And we can graph that below. -1/3, it's going to be to the left of the x-axis. And 128/27, that's just a little bit less than 5. So we get a point about right here. All right, and also feel free to label it -1/3, 128/27. All right, so we could try to connect the dots right here, but I do want to kind of do our sign chart so we see exactly what's going on here. I'm going to put it right here. So there's some space. So when you're building your sign chart, what I want you to do is draw a line that kind of represents the x-axis. And I want you to do a mark for each and every critical number and PPI. So we had a critical number at -5/3. Draw them in ascending order. We had a PPI at -1/3. And then we had a final one at 1, right? And consider what the second derivative does with these functions, at these values here. Now, -1, so the second derivative was a linear function, remember? We saw it above right here. It was 6x plus 2. And because it's a linear function with a positive slope of 6, it'll be increasing, and for always. It'll be below the x-axis until it hits its intercept, which is -1/3, and then it'll be positive forever afterwards. All right? And so interpreting this right here, we have negative, negative, positive, positive. So if we think about our critical numbers, because it's concave down, so it's going to be concave down at this interval right here, it's concave down at -5/3. That means you have a sad face. Oh, how sad that is. Because it was concave down at a critical number. On the other hand, at x equals 1, it's concave up because we have these positive values right here. In which case we draw a little happy face. He's so happy to see us. And so it's concave up, and it's going to be positive right here, meaning that we have a local minimum at 1. We have a local maximum at -5/3. And if we think about what is the first derivative doing right here, if you have a local maximum, that means it was increasing, then decreasing, decreasing, and then increasing. And so we want to put all this together, right? Make sure we have all the appropriate behavior about monotonicity and concavity. So this point of inflection is going to happen at -1/3. It's going to be increasing, decreasing. I often like to draw the picture from the inflection point. So to the left of -1/3, it should look like it's concave down. -5/3 is a local max. Whoops, kind of missed it there. Whoops-a-daisy. Also got a little extra inflection that I didn't need there. Let me try that again. So we're concave downward. We have a local maximum. Oh, I missed it again. Oh well. So you can see the behavior here that it was increasing and then decreasing because we had a maximum, and then it's concave downward in this region. Then when you get past -1/3, it should be concave up. You'll be decreasing until you hit 1, and then you can be increasing after that. All right? And so now we have a pretty good picture of our graph here, our polynomial. Now, what I actually have on the next page is a computer-generated image of what we just created here. And you can see that, hey, I think I did pretty okay. Not the best drawing I've ever done in the world. Certainly is not the worst either. But we can see that behavior we were seeing before. We see that it was concave down right here. It was concave up right here. We found that point of inflection. It was increasing, decreasing, increasing, because we found this max and this min. And so we found all this information just from the formula. And so our graph is actually fairly accurate compared to what we had on the computer. Let's do another example. This time we have a rational function. F of x equals x plus 1 over x. So what are issues we have to do with here? Well, because of the denominator, there could be issues that make this thing undefined. And so if we think about the domain of this thing, the domain is going to be everything so that the denominator doesn't go to 0. So basically, we have to throw out x equals 0. That's not inside of our domain. Now, I often like to do domain with the discontinuity category together because problems with the domain often are associated to discontinuities. I mean, after all, to be continuous, your function has to be defined. The limit has to exist, and the limit and the function have to agree. Well, if you're undefined, that's already an indication of a discontinuity. So what's going on there? Well, as we approach x equals 0 from the right, if we take the limit here of our function f of x, well, as you approach 0 from the right, you're going to end up with this 1 over 0 plus, which is positive infinity. And as you take the limit as x approaches 0 from the left of f of x, you're going to end up with 1 over 0 minus, which looks like a negative infinity. And so this is indication that we have some type of vertical asymptote at the y-axis. We'll put this on the screen a little bit later. In terms of intercepts, right? Well, because x equals 0 is outside the domain of the function, turns out there is no y-intercept, right? The y-intercept does not exist. In terms of x-intercepts, well, if we looked at the equation f of x equals 0, this would imply we look at x plus 1 over x equals 0. This gives us that x equals negative 1 over x. Give myself a little bit more space there. Times both sides by x, you get that x squared equals negative 1. I'm going to stop you right there. X squared can't equal negatives. It has to be non-negative. If we were to take the square root, we're getting some imaginary numbers at that point. So this tells us that x-intercepts also do not exist. So this graph has no x-intercepts nor y-intercepts. That might seem like bad news, but this is actually great news because if you have no x-intercepts or y-intercepts, this tells us that we can never touch the x-axis or the y-axis. That's going to help us draw our picture actually quite well. In terms of symmetry, this graph does actually have some symmetry. I normally don't care about it, but if you look at f of negative x, you end up with negative x minus 1 over x, which if you factor that out, x plus 1 over x, that is, factor out the negative 1, you end up with negative f of x. So this indicates that our function's odd. And so if we were graphing it, it should be symmetric with respect to the origin. All right. So let's see. In behavior, this one's a good one to know as well. If we take the limit as x goes to infinity of the function x over 1 over x, well, what's going to happen as x goes to infinity, the 1 over x is just going to go to 0. It's going to vanish. And so this thing will just look like the limit as x goes to infinity of x. And as this is a polynomial now, it'll just look like infinity. And similar things will happen as we take the left side, take the limit as x goes to negative infinity of x plus 1 over x. Same things happen as before. The 1 over x will go to 0, and this thing will look like the limit as x approaches negative infinity of here, x. This will go to a negative infinity. And in fact, this graph has what commonly be called an oblique asymptote. This is some diagonal line where our function f of x will be approximately the same thing as x as you go to the extreme. So we're going to actually add that oblique asymptote to our graph in just a second. Let's look at the derivative first. Well, actually, now that I moved down a little bit, I guess we are kind of in the right spot to start graphing this thing. So what did we say earlier we had? So we have this oblique asymptote, which is the diagonal line y equals x. We get something like that. And we get something like that. And then we also had a vertical asymptote at the y-axis. There was no x-intercepts, no y-intercepts, but we have these we do have these asymptotes right here. So we're going to find some critical numbers by looking at the first derivative. Y prime is going to equal 1 minus 1 over x squared. If we set this equal to 0, we end up with 1 equals 1 over x squared, which gives us x squared equals 1, which gives us x equals plus or minus 1. So we get some critical numbers at plus or minus 1. I mean, critical numbers, we also should be worried about where does the derivative not exist, which there's the same domain issues we had before. If x is 0, you're going to divide by 0. But don't worry about that necessarily. Because the original function was undefined at 0, the derivative will also be undefined at 0. And that's not a critical number. That's just a discontinuity from before. And so let's add these critical numbers to our graph here. If we take x to equal 1, plug 1 into the original function, you're going to end up with 1 plus 1 over 1, which is 2. And so we're going to plot that point there. We're going to get x is 1, y is 2. So we get a point right here, 1, 2. I want to figure out what happens at -1, which we could plug that into the function as well, but we can also use symmetry. Since we know it's odd, we know there's going to be a point right here at -1, -2. These are our critical numbers. For the second derivative, we take the derivative of this bad boy right here. And so that's going to give us positive 2 over x cubed. In which case, that actually never equals 0. If you have a fraction equal to 0, it's because the numerator was equal to 0, which here the numerator is 2. There are problems at x equals 0, but again, that's a discontinuity. That's not a point of inflection. So what this tells us is that the derivative could change its inflection at 0, so we do care about it. I mean, don't be ignoring it. The first and second derivative are undefined at 0, and so that's going to come into our sign chart that we're going to build right over here. So the numbers we want to care about are -1, 0, and +1. And so what does the second derivative do at these locations? Well, looking at the function 2 over x cubed, 2 is always positive. X cubed will have the same sign that x does. And so when x is positive, the second derivative will be positive. And when x is negative, the second derivative will be negative there as well. So we have a minimum at -1. We have a maximum at x equals 1. And because you went from a negative to a positive, this indicates a change of inflection, right? When you're less than 0, your graph will be concave down. When you are greater than 0, you're going to be concave upward. And so putting this all together, let's take our point 1, x equals 1 here, which is going to be a local minimum. The graph has to approach infinity when you're to the right of 0, and it has to approach this asymptote as well. And so we get this concave up picture right here. It went from decreasing to increasing because it's a local minimum. And then by symmetry, we're going to get the same type of picture down here. When you do these curve sketches, you often get more information than's actually necessary to draw the entire graph. Those type of redundancies are okay. We like them because it helps us get a better understanding of the graph right here. And so this is our final picture. Let's see how we did. The next page, we can look at a computer-generated image right here, and voila, we have exactly that picture. We see the two little cup shapes. One is concave up right here. The other one's concave down right here. It was increasing, then decreasing. It was decreasing, then increasing. The oblique asymptote is illustrated. I did not include the vertical asymptote here just because it's the y-axis, and so you can't really see it very well if I were to draw it there. So we did pretty good. Let's see. Looking at the time, we have time for one more. Let's do another rational function right here. So take the function f of x equals 3x squared over x squared plus 5. So I always like to start with the domain. Because it's a rational function, I care about what makes the denominator go to 0. X squared plus 5 equals 0. That would imply that x squared equals -5, and whoop, JK. X squared can never equal -5, right? That's some imaginary number. This tells us that our domain is going to be all real numbers, -infinity to infinity. Okay? Now, if we jump to discontinuities, for a rational function, the only way you'll have a discontinuity is if your denominator goes to 0. So since this denominator never goes to 0, this function has no discontinuities. That is to say, it's always continuous. Always continuous. All right. And let's see, moving on to the next piece. In terms of intercepts, I do care about that. Intercepts. Looking at the y-intercept, you get f of 0. This will equal 0 over 5, which is 0. In terms of x-intercepts, we want to set the function equal to 0, 3x squared over x squared plus 5. Now, like I said just a moment ago, if a fraction equals 0, it's because the numerator equals 0. You can multiply both sides of the equation by the denominator, x squared plus 5, and do the other side as well. X squared plus 5. Well, of course, if you times anything by 0, that'll just be 0. And on the right-hand side, they cancel. So we end up with just 0 equals 3x squared, which will imply, because you can divide by 3, take the square root, that x equals 0 itself. So this is our x-intercept. It was also a y-intercept. So this function is going to go through the origin. If we looked at symmetry, f of negative x, this will equal 3 times negative x squared over negative x squared plus 5. If you take a square of a negative number, it becomes positive. So you get 3x squared over x squared plus 5. That's equal to f of x again. This function is even. It's symmetric with respect to the y-axis. If you skip this step, it's not a horrible thing, but it is an even function. Let's use that to our advantage. In terms of end behavior, take the limit as x approaches infinity of our function 3x squared over x squared plus 5. When you have a rational function, to determine the end behavior, you want to think of who's the dominant term, like who's the fastest growing function on the top and bottom. Well, the numerator is only 3x squared, so that's what's going to be there. And on the bottom, you have an x squared as well. So this is what we would call a balanced ratio. And so in terms of the end behavior, you only have to look at the leading terms. And so this will look like 3x squared. Sorry about that. 3x squared over x squared as x goes to infinity. The x squares basically cancel out, and this will just look like 3. That is y equals 3. We have a horizontal asymptote. Now for rational functions, the end behavior on the right, if it's a horizontal asymptote, will match that on the left. So if we did the same thing here, 3x squared over x squared plus 5. In terms of end behavior, only the dominant terms matter. So you get 3x squared over x squared. The x squared cancel out again. You still end up with 3. And so this is going to be the same as on the left and on the right. All right. Now, with this rational function, the derivatives are going to be a little bit more challenging to calculate. So be patient with me here. The quotient rule is going to be necessary as we look for y prime. So by the quotient rule, sing the song if you have to. So we're going to take low, x squared plus 5, d high, 3x squared prime, minus high, d low, square the bottom, and here we go, x squared plus 5 squared, right? And so the derivative of the 3x squared, that's going to be a 6x times x squared plus 5. And then the derivative of the x squared will be a 2x. So that gives us 3x squared times just 2x. This sits above the denominator still. We're going to leave the denominator alone. Don't multiply it out. It never does you any benefit to do that. Leave denominators factored. They like that way. In which case, if we keep on going, let's see, where were we? If we keep on going, I'm noticing there's a common factor of 6x on the top and bottom. On the top. You have a 6x right here, and then you have 3 times 2x. If you take out the 6x, because we do want this thing to be factored, that'll leave behind x squared plus 5, and then we get minus just an x squared, for which we see that the x squareds are going to cancel. That's kind of convenient. And this still sits above the denominator, x squared plus 5 squared. Simplifying that a little bit more, you get 6 times 5, which is 30. So you get 30 over x, 30x times x squared plus 5 squared. And so in terms of critical numbers, you're going to end up with just 0. Because if 0 is what makes the numerator go to 0, and the denominator never goes to 0 in this situation. The second derivative is going to be a little bit more involved here. Let me actually let's see how much space we have right here. It's a little bit crowded, so I'm going to bring it down here. It's really helpful. It's really helpful to simplify your derivative as much as possible before you go on to the next step. So if we were to carry this on down here, well, that's kind of too much. We want to bring it up over here. So for the second derivative, again, using the quotient rule, we're going to get low, d high, take the derivative of the top, you get 30, minus high d low. So by the chain rule, you get 2x squared plus 5 times 2x. This all sits above your denominator, which is x squared plus 5 to the 4th, because we just squared it. Let's try to simplify that. There is a common factor of x squared plus 5 here and here. So factor that thing out. Can we factor anything else out of the fraction? Just give it a quick inspection there. I guess you take a 30 out. That's also acceptable. So we get 30 x squared plus 5. What leaves behind? X squared plus 5. And then we have a 4x squared, I think. No, that should be negative. My bad. From the negative sign that happened earlier. So that'll be a negative sign. And this sits above our denominator, x squared plus 5 to the 4th. Now, because we took out an x squared plus 5 on the top, we can lower this power by a little bit. We should combine these x squareds to give you a negative 3x squared. And then from that, I think we have a pretty good second derivative. Let's find a little bit more space here. For which case we're going to get 30 times 5 minus 3x squared all over x squared plus 5 cubed. And so our potential points of inflection this time around will look like we have to set this guy equal to 0. And if you do that, you're going to end up with plus or minus the square root of 5/3. Like so. And so we want to build our sign chart from this. So let's take our PPIs. So we have this negative square root of 5/3. We had 0 as a critical number. And then we had positive square root of 5/3. What is our second derivative doing right here? So if we pick something less than, if we pick something like I'd say at 0, right? At 0, this thing ends up being positive. So we get positive and positive. If we pick something greater than the square root of 5, it's the square root of 5/3, we'll get something negative. And then over here, we also get something negative. We plug some values in there. So this tells us that we're going to have some type of minimum value at 0. It's concave down, then concave up. It's still up, and then concave down. And so let's try to put all this information back onto the graph that we had. So if we plug in x equals 0 into the original function, we're going to get 0. We had it was an x-intercept and a y-intercept. Square root of 5/3, that's approximately 1.29. And if you put that into the function f, you're going to get like 3/4 approximately. So it's not a really high point. You're going to get something like right here if you do that point of inflection, and then you get the other point of inflection basically over here. We had, remember, a horizontal asymptote at 3. So we get some examples like that. And if we use the notions of concavity and monotonicity, we had a local minimum at 0, and it was concave upward at that location. And so then at these other points, it's points of inflection, the concavity will change. It should be concave down as it approaches this horizontal asymptote, like so. And so this gives us our graph. Let's see what the final result looks like. Computer-generated image gives us something like this. Hey, that's pretty good. Pretty good. And so looking at the time, that's about it we have for right now. You can see that these curve sketch examples can take a while to do. We got through 3 examples in about 50 minutes. I want to do some more examples of that, and we'll do that next time in lecture 37. See you then. In the meanwhile, if you have any questions or comments, please post them in the comments below. If you'd like a script of what we talked about today, you can find that in the description under the link to my Google Drive. And again, I'll see you next time. Bye.